All right, so this is problem 6.5 from lecture number 22. And here we have this uniform bar and these wheels, and the bar starts out from rest and then it falls down. And the question is, as it falls from 60 degrees to 45 degrees, how fast does it end up moving? And the way you want to look at this first to see if it's an energy problem is to make sure that there's no friction lost and it rolls without slip. So we're not losing friction here, and we're going to assume that these bearings are nice and frictionless as well. So what we're going to do is we're going to think about, okay, all of these bodies are going to have some energy at the beginning, and that energy is, we'll think of that as the potential energy, and it's going to lose that potential energy and transform it into kinetic energy. So some potential energy is transforming to kinetic energy. And the potential energy, we can just write the same as we always would. We're going to have some mgh term, where the h is going to be here. So that's going to be the sine of theta times the length for this wheel. And then for the bar, we only have to go half the length up. So we're only going to need one half mg times this height. And this wheel, its potential energy is not changing because it's always going to be on the ground. We're assuming that like gravity is down like this. So that wheel isn't moving. We don't have to worry about that. And now let's think about the kinetic energy. So the kinetic energy, we're going to be summing for all of these components some sort of 1/2 mv squared plus I bar omega squared term. And we know that we can't neglect the angular velocity because the bar is going to be rotating, and it's actually pretty heavy compared to the wheels, and the wheels are going to be rotating, and we don't want to neglect their angular velocity either. So we're going to have this expression that's going to have all these terms, but in order to solve for what one of them is based on this change in potential energy, we're going to need some relationships between the angular velocity and the velocity. Oh, and how perfect. This is what kinematics is for. So the velocity of wheel A, we know that's going to be equal to the angular velocity of wheel A times the radius r if it's not slipping. And the radius we're talking about here is not the radius of curvature, but it's a 6-inch deal. And then for ball B, we're going to have the velocity of V, the velocity of point B, VB, is going to equal the angular velocity of B times the radius r. Now, getting the angular velocity and the velocity relationships for the bar is a tiny bit trickier. We can think about it with this equation that the velocity of some point on the bar is going to be equal to VA plus omega crossed with some position vector. Or we can think about it geometrically that like this distance here between the ground, this origin point, and this point A is going to be SA, and that's going to be equal to L cosine theta. And then when you take the derivative of that, then you'll have VA is going to be negative L theta dot sine theta, just by taking the derivative and using the chain rule. And remember, this theta dot is going to be the rate and change of this angle, so it's going to be the angular velocity of the bar. And you could do the same thing for B, right? Okay, so now we're going to have a bunch of expressions. We can start kind of thinking about specifically what that means for this problem. So for this problem, the change in potential energy, we're going to have the mg of the wheels times L times the difference between sine 60 and sine 45. And then we're going to have the change in the potential energy of the bar, so the mg L over 2 difference. And then we're going to have our kinetic energy terms. So let's start with the wheels. We're going to have the wheel is going to have some mass, and then it's going to have some velocity, and we're going to square that. So the velocity is going to be for wheel A, it's going to be here, L theta dot sine theta. So we're going to have L theta dot sine 45, and we're going to square that, multiply it times the mass. And then we're also going to have the angular velocity of the wheel to take care of. So we're going to have that I term, I about the center of mass, which is going to be mass of the wheel times k squared plus the angular velocity, and the angular velocity is just the velocity divided by r. So, and we'll square that. And then, but then if you look at this, for this particular problem, each of the wheels is going to have the same velocity at 45 degrees, right? Because sine 45 and cosine 45, they're the same. So actually we can multiply this whole thing by 2, which is going to simplify our math a little bit. And then, okay, now let's look at the bar. Now we could do the same kind of formulation where we're going to have the 1/2 mv squared plus I omega squared. But in this case, there's kind of conveniently, we can see that the instantaneous center is going to be here, because you're going to know that this VB is moving up and down this way, and it's going to have some distance here, and this one's moving this way. So like the intersection of those two perpendiculars from the velocity is going to be here. And conveniently, this distance is going to be the same as this distance, right? Because this is going to be in the center. We drew a line here, right? Like you could see by symmetry that this distance is going to be 1/2 the length. And so we already know that for a bar rotating about this point, it's 1/3. And so this is the same for a bar rotating about this point. So now we know that our I about the point of instantaneous center here is going to be 1/3 mass of the bar times the length of the bar squared. So we can just substitute that right in here in our 1/2 I omega squared term. All right, so now we have an equation for how we can solve this, and everything is in terms of theta dot. So all we need to do is solve for theta dot. So then here, let's see, it's kind of got a little bit messy, where we're going to take mg of the wheel is going to be 12 times 4, so that's this distance L, and we're going to keep everything in slugs times feet per second squared times feet again. So this is already in good units because we can use this as mg. And then we have this difference. And now we're going to kind of simplify a little bit here. We're going to remember that we want the mass here in slugs. So we got to divide that by 32.2. And then these half and this 2 cancel out. So we're not going to worry about that. We're going to combine. We're going to notice that all these terms are the same. So we just have the mass, the length squared, the sine 45 squared, and then we just have to add to that this k squared over r squared term. So we're going to have the mass, the length squared, the cosine or sine 45 squared, 1 plus k squared over r squared, which in this case we can substitute that 4.5 and that 6 in inches, because this is in inches and this is in inches, so the fraction will be the same, times r omega squared. And then for this term we simply do the same thing. We're going to multiply 1/2 times 1/3 and get 1/6. And we've got 40 over 32 for our mass, and we've got 4 squared and theta squared. So if you actually get the numbers here, we're going to have 20.34 equals 46.58 theta dot squared plus 32.12 times theta dot squared. So when you solve that, you do in fact get this answer. I guess the one thing to be aware of is that when you use energy methods and they ask for a vector quantity with a direction like this, then you are going to have to kind of reason out which direction it's going to be. So let's do a little bit of that. So we know that it's going to be falling down. So this point will be rotating this way. This point will be rotating this way. So here's our VB, here's our VA. And so if you picture that, it's rotating in this direction, which is the same as a clock, so clockwise. So there we go. Thank you.